Okay, hello everyone. I'm Andrew Lewis-Pye. I'm going to talk about our recent paper, The Economic Limits of Permissionless Consensus. So this is all joint work with Eric Budish. Eric's an economist at the University of Chicago, and with Tim Roughgarden, who's a professor of computer science at Columbia University and also head of research at ACCZ. Okay, so the topic of our paper is something that's been of interest in blockchain circles for a while now. So specifically, we're interested in the incentives around and costs of 51% attacks. Okay, so presumably everybody's familiar with the idea of a 51% attack. Okay, if in the context of Bitcoin, if an adversary controls 51% of the hash rate, right, then they're in a position to roll back the finalized transactions, to cause a double spend, or what we might call a consistency violation. Right? So that's in the context of Bitcoin. Many proof-of-stake protocols, it's the case that if the adversary controls a third of the resources, a third of the stake, then they're in a position to launch a similar attack. Okay, so the question we're interested in is what happens when we find ourselves in this scenario where the adversary is large enough to carry out an attack of this sort. Right? Is our protocol then useless? Should we just give up? Or are there things we can do in this sort of scenario to disincentivize such attacks from happening? Okay, so if the adversary is large enough they can carry out an attack of this kind, why wouldn't they just do that? Right? And actually, this is something that Nakamoto considers right back in the original white paper, in the Bitcoin white paper. His argument goes something as follows. Okay, so if the adversary has 51% of the hash rate, right, then they're in a position to earn lots of future Bitcoin rewards. Right, if they earn 51% of the hash rate, if they're just honest, then they can expect to get 51% of future rewards. On the other hand, if they carry out a double spend, if they cause a consistency violation, and that can be expected to cause a significant and sustained drop in the dollar value of Bitcoin. And that would mean that their future rewards are worth much less. Right, so the hope is that this should be enough to disincentivize the attack from taking place. So that's the original argument. Nowadays, there's a modern spin on that because nowadays to participate in Bitcoin, you have to invest in this specific hardware, right, in ASICs. It's hardware which is useful for mining Bitcoin and not really useful for much else. So now the argument goes as follows. So if the adversary now has 51% of the hash rate, then they must be heavily invested in these ASICs. If they carry out a double spend, then it's a choice the community can make to do a hard fork and to change the cryptographic hash function. Right? And if they do that, then the ASICs will now be worthless. Right? Okay, so again, the hope is that this threat should be enough to disincentivize attacks from taking place. Okay, so maybe both of these arguments have some merit to them. A basic sort of problematic aspect of both of these arguments, though, is that they apply a scorched earth style approach to punishment. Right? So it's true in both these scenarios that the adversary is harmed, right, either through a drop in the value of the currency or because their ASICs are now worthless. It's true the adversary is harmed. It's also true that all the other honest participants are also harmed. Okay, so this raises then an important and natural question. So, are these issues fundamental to permissionless consensus? Right? So is a scorched earth style approach to punishment, is that the best we can do? Or are these issues really just specific to Bitcoin's design decisions? In particular, the fact that it's a proof of work protocol, maybe. Okay, well, if we're not going to use proof of work, then the next most obvious alternative is proof of stake. Right? And immediately with proof of stake, things look different. Right? With proof of stake, one of the fundamental differences, as distinguished from proof of work, is that now the underlying resource, the stake, is controlled by the protocol. Right? Now it's on-chain rather than being off-chain. Okay, so at a high level, the idea now is as follows. Right? The hope is as follows. So if the adversary carries out a double spend, if they cause a consistency violation, then hopefully it's going to be the case that somehow the protocol is able to reach out and surgically confiscate the stake from the attacker and not from other honest participants. Right? To leave them unharmed. Okay, so at a high level, hopefully that idea sort of makes some sense. If you actually sit down and try and think about how you'd actually design a protocol that carries out this though, there are a number of basic obstacles. Right? So the first basic obstacle is hopefully clear. So if we're going to surgically confiscate stake from the attacker and not from honest participants, then we better, the protocol better be able to point to exactly who the attacker is, right? So that the protocol better produce what we might call proofs of guilt or certificates of guilt that point to the attacker and which don't point to other innocent parties. As it turns out, though, this isn't actually too hard, right? So actually, many protocols, many BFT-style protocols anyway, naturally achieve this for you. Right? They provide these kind of proofs of guilt in the event of a consistency violation. Okay, so that's the first thing we need, but that in itself is not enough, right? If we're actually going to punish the attacker, then it also better be the case that honest players receive these proofs of guilt quickly, or at least reasonably quickly. Specifically, they better receive these proofs of guilt before the adversary is able to cash out of their position and run away. Okay, so there are some sort of timing considerations here. That's one thing we need, and then another thing we need, if we're going to actually punish this attacker, right, then we need to reach consensus on who we're punishing. Right, so it may be the case that the protocol produces these certificates of guilt, but different players, different participants might receive slightly different versions of these pointers, slightly different sets of players. Okay, so we need to reach consensus on who we're punishing. And beyond that, also, presumably, once we've seen this consistency violation, we don't want to start again right from the genesis block. We have to reach consensus on where we're going to start and restart from as well. Okay, so we need to reach consensus on who's been punished and from where we should restart after consistency violation. And the difficulty here is that all of this is taking place in a context where the adversary is apparently large enough that they can cause consistency violations, right? So they're apparently mucking up our consensus protocol, right? So if they're large enough to cause problems in the first place, it's not immediately clear, okay, that we're now going to be able to reach consensus on who should be removed. Okay, so obviously one important case study is Ethereum. Ethereum made the transition from proof of work to proof of stake. And one of the main reasons they cited for doing that was this idea that proof of stake should offer greater crypto-economic security than proof of work. So this raises natural questions. So first of all, is proof of stake actually more economically secure than proof of work? Before we can answer that, though, we need to know, okay, what even does that really precisely mean? Right? Obviously, we're going to study these things in a formal setting. If we're going to prove theorems, we need a precise definition of economic security. Okay, we're not just interested in writing down a precise definition and then looking at one protocol after another and determining whether or not it satisfies the definition. We're also interested in exploring the design space more generally. Right? So we're interested in questions like, could there exist protocols more secure than today's Ethereum? Okay, and another thing we naturally have to be interested in is how the answers to all these questions depend on our basic set of assumptions. Okay, so whenever we're working in distributed computing, there are various different possible set of assumptions we can make in terms of how reliable we assume message delivery is, that sort of thing. And generally expect our answers to depend, sometimes quite substantially, on those assumptions. Okay, so I said there, obviously, if we're going to study this stuff in a formal setting, we need a precise definition of economic security. So the first thing we do in the paper is to write down such a definition. Right? We define what we call the EAC property. Okay, so here EAC stands for expensive to attack in the absence of collapse. So even expensive to attack, even if there's no collapse in the value of the currency. So in this talk, I'm not going to go through the precise details of the definition because there are some fairly nuanced of economic considerations there. I'm going to give us a high-level version of the definition. Right? So for the purposes of this talk, you can think of EAC as just meaning the following two things. So first of all, the protocol should have this property that honest players never lose resources. Okay? So in particular, in the case of a proof-of-stake protocol, it shouldn't be the case that honest participants get slashed. So first of all, honest participants don't lose resources. And secondly, in the event of a double spend, the attacker should be guaranteed to lose resources. Okay, and preferably a significant amount of resources. Okay, so once we have a formal definition, then of course we can start proving formal results. Okay, so in the paper we prove three main results. There are two impossibility results and then one possibility result. Okay, so I'm going to state those results next. Before we do that though, let's go to see some basic definitions. So by a row-bounded adversary, we mean one who controls at most a row fraction of the resources, whatever those resources are, we don't care, right? So it could be stake, hash rate, in the case of a proof of space protocol, it could be memory. And then we have to be precise about our assumptions regarding message delivery. Okay, so this is the definition of the standard synchronous setting. Okay, so in the synchronous setting, message delivery is reliable, or more precisely, there's a known bound delta on message delay. Okay, so if a message is sent at time t, it always arrives by time t plus delta. At synchrony, for partial synchrony, okay, message delivery is sometimes reliable, sometimes not. Or more precisely, so we're guaranteed arbitrarily long periods during which messages always arrive within known bound delta. Okay, but there may also be arbitrarily long periods during which message delay is not bounded. Okay, so basically most of the time, maybe, or a lot of the time, message delivery is reliable for arbitrarily long periods, but there can also be unbounded network partitions. Okay, so in practice, what that means basically is that our protocol has to be live at least during periods of synchrony, right, when message delivery is reliable, but it has to maintain consistency at all times, even during these sort of asynchronous periods where message delivery is not reliable. Okay, so we're going to, as I say, we're going to state 3 main results, 2 impossibility results. Before we do that, though, it's worth noting the following. So actually, if the adversary is sufficiently bounded, they can't cause consistency violations anyway, right, then a protocol will be EAC has a trivial sense, right? So if we're thinking about a proof of stake protocol in partial synchrony, and if the adversary controls less than a third of the stake, say, okay, then they're small enough, they can't cause consistency violations anyway. Okay, so the protocol will be trivially EAC in that context. So our goal here, right, is really we want to produce protocols that are EAC beyond the security threshold. And that's the interesting regime. Okay, so here's our first impossibility result then. Okay, so let's consider the synchronous setting, right, in which message delivery is reliable. So as I say, this is an impossibility result. So working in the synchronous setting, like the easiest possible setting, just makes the result as strong as possible. Okay, so in the synchronous setting, the result then says this: if the adversary can control half the resources or more, then no longest chain protocol can be EAC. I should be clear here, I'm giving a slightly informal version of the theorem. Okay, this can be formalized using the permissionless hierarchy framework that I've developed with Tim. Let me go through those details in the paper. Should also hopefully be clear that this result is tight, basically because if the adversary controls less than half the resources, then we can stop them causing consistency violations anyway. Right, so the protocol is sort of trivially EAC in that sense. Yeah. Okay, so in particular, Bitcoin is trivially EAC if the adversary is row bounded for row less than a half. They control less than half the resources. Okay, so what the theorem is saying here is that there are really only 2 regimes of interest, right? So on the one hand, if the adversary is sufficiently small, they control less than half the resources, then we can ensure they can't cause consistency violations anyway. On the other hand, as soon as they're large enough to cause consistency violations, they're large enough to stop any longest chain protocol being EAC. So that's our first negative result. Okay, that's for longest chain protocols, or more generally for dynamically available protocols. This result holds as well. Okay, so now for our next result, let's make things a little bit easier by not restricting ourselves to longest chain protocols and dynamically available protocols. Okay, let's consider general protocols. In particular, we're now allowed to consider BFT style protocols. Okay, so let's make things easier by considering general protocols, but we'll make things harder by moving from the synchronous setting to the partially synchronous setting. Okay, so now the result is as follows. If we're in the partially synchronous setting, and if the adversary can control a third of the resources or more, then no protocol, even BFT style protocols, can be EAC. Okay. So when we move from the synchronous setting to the partially synchronous setting, the relevant threshold changes, relevant security threshold changes from a half to a third. Right? If you're in the synchronous setting, then protocols can be live and consistent if the adversary controls less than half the resources. If in the partially synchronous setting, that's true, they control less than a third of the resources. Okay, so that means this result here, that the third bound is tight. Okay. If the adversary controls less than a third of the resources, then we can just stop them causing consistency violations anyway. And actually, a stronger thing can be proved here. Okay, actually, you can't punish in the event of a consistency violation at all, even if you allow collateral damage. Okay, so again, what the theorem's saying here is that there are only 2 real regimes of interest, okay, in this setting. Well, either the adversary is small enough that they can't cause consistency violations, or If they're large enough to cause consistency violations, then they're already large enough to stop the protocol being EAC. Okay, so those are our two impossibility results. To get a possibility result, right, we could keep on working with general protocols. So again, in particular, we're allowed to work with BFT style protocols. And we could just move to the synchronous setting. Okay, we could show that it's possible to be EAC in some non-trivial way for BFT style protocols, for example, and in the synchronous setting. Okay, we could do that, but actually we want to do more than that, right? So ideally, what we would like is protocols that give all the normal guarantees in partial synchrony. Okay, so if the adversary is sufficiently bounded, if they control less than a third of the resources, then we'll get everything we normally have. We know that it can't satisfy the EAC property, we've just seen that. Okay, but it should give us all the standard guarantees. Then what we'd like is that actually the protocol will be EAC beyond the security threshold in some non-trivial way if synchrony happens to hold with respect to some much larger time bound, some time bound potentially much larger than delta. Okay, so that's ideally what we'd like. And our positive result basically says precisely that we can do that. Okay, so for this result, we consider two different parameters, delta 1 and delta 2. And you can think of delta 1 here as being quite small, maybe of the order of a second or a few hundred milliseconds or smaller. Delta 2 you can think of as being arbitrarily larger than delta 1. And what we can show is that there exist BFT-style proof-of-stake protocols. First of all, they give us all the normal guarantees in partial synchrony. Okay, they'll be live and consistent as long as the adversary controls less than a third of the resources. Okay, and also they'll have latency, right? They'll finalize transactions in time, which is like a function of delta 1, the small parameter. Okay, but these protocols also give us the guarantee that they will be EAC, right, if synchrony happens to hold with respect to this much larger time-bound delta 2, as long as the adversary is row-bound for row less than 2/3. And it's worth noting here that we don't really require synchrony to happen to hold at all times with respect to large bound delta 2. We just need it to happen around the time, and we need that to hold around the time of a consistency violation. So the 2/3 bound here is basically it's the best possible. This follows from a result of Tacitel from 2003. So that's tight unless you're willing to give up some liveness resilience. Okay, so if you're prepared to make the protocol easier to attack in terms of liveness, then you can actually push this 2/3 bound up as close towards 1 as you like. Why does the 2/3 bound hold in general? Basically, that's because if the adversary is larger than that, then basically they can take complete control of the protocol. They can just finalize blocks and so on without help from any participants. So that's where the 2/3 bound crops up. Okay, so previously we only have had two regimes of interest in the previous settings. Yeah? Now we have three regimes of interest. Okay, so first of all, if the adversary is less than a third of the resources, if they're quite small, then we can just stop them causing consistency violations. Once they control more than a third of the resources but less than 2/3, then the protocol can be EAC. Okay, but if the adversary is large enough and they control more than 2/3 of the resources, then the protocol cannot be EAC. Okay, so to recap those results then. So we've seen that being EAC is not possible for longest chain protocols, and actually this result holds more generally for dynamically available protocols. We've seen that satisfying the EAC property is not possible in partial synchrony. On the other hand, we can build BFT-style proof-of-stake protocols to give all the normal guarantees in partial synchrony, okay, and which also satisfy the EAC property if synchrony happens to hold with respect to some large time bound. Okay, so to finish off the talk, I just want to talk about some follow-up work which considers liveness attacks. Okay, so far the whole talk has been about what we do in the event of consistency violations. Okay, in this follow-up, we move on to consider liveness violations, and everything here in this follow-up work, this is all joint work with Joachim, Tim, and Luca. Okay, so when we talk about liveness violations, I want to focus in particular on the question of accountability. Okay, so the question there is, can we produce, or when can we produce, proofs of guilt for some guilty parties in the event of a liveness violation? And basically the reason for that particular focus is because actually we've already done a lot of the hard work, right? So actually once we have accountability, the same techniques as for consistency violations can be used to achieve the equivalent form of EAC. Okay, so it's really the accountability part we have to be interested in now. A basic sort of intuitive observation here is that liveness accountability would certainly seem to be harder than accountability for consistency violations, right? Right, with consistency violations, often they'll be caused by people like sending too many messages. Right? It might be the case you vote for one block and then you're naughty and you vote for an inconsistent block that you shouldn't be voting for. Right? On the other hand, liveness attacks typically involve not sending messages. Okay, so this is a basic question here. Okay, how do you prove the absence of messages in order to produce these proofs of guilt? Okay, so I don't have very much time to talk about it here, so I'll just give some sort of highlights, right? So we prove a bunch of negative results to focus briefly on the positive result we prove. Okay, basically what we show is, that basic intuition is correct. Accountability for liveness violations is harder than for consistency violations. On the other hand, there is some positive stuff you can do. Okay, so in particular, we prove a result that has a sort of a similar form to the positive result we saw earlier on. Okay, so there exist protocols that give all the usual guarantees in partial synchrony if the adversary is sufficiently bounded, if they control less than a third of the resources. Okay, but which also provide liveness accountability if some stronger guarantees on message delivery hold, okay, and if the adversary is row bounded for row less than a half, so they control less than half the resources. Okay, so here I'm stating out an informal and imprecise version of the theorem statement. Obviously, if you're interested in the precise details, I encourage you to check out the paper, which is called Accountable Liveness. Okay, so that's the positive result, and then we prove some negative results, which establish precise senses in which the positive result is tied. Okay, so that's all I have time for today. I hope you find the topics interesting, and thanks for listening.